welcome grade 12s. Today we're looking at work, energy and power. That section we know that when it comes up in the exam you go, no, I hate this section. It's actually a really nice section. You are going to get it, and remember the thing that we're really harping on at the moment is the work energy theorem. So quickly before we go into the actual questions that we've got planned, I just want to remind you of some things. So remember, work and energy are pretty much interchangeable. Work is defined as a force times by a distance cos theta. Remember, the angle that the force acts on is very important. Energy is defined as the ability to do work, and then of course power is the rate at which work is done. Now power, you have two equations, power equals W over T, and you have F times V. F times V is actually a nice equation, but it is only valid when you have a constant velocity. If the object changes velocity, in other words, its kinetic energy changes, you cannot use P equals FV. Be very careful, they're going to try and trick you out with that one, okay? Then you have to use W over T. For the work energy theorem, and this is the one that we know you guys don't really like, work energy theorem says to us that the net work done on any object is equal to the change in kinetic energy. Some of you might have learned it as change in EK. That's fine. K is the symbol that's on your information sheet at the moment. Guys, that's very important because you're going to get it. Kinetic energy, remember, changing kinetic energy means I've got to do kinetic energy final minus kinetic energy initial. Okay, any change in, whether it's in equations of motion, momentum, whatever the case may be, it's always final minus initial. That's very important. Okay, so are you guys ready to jump into the first question? It's actually a really nice one. It's taken from the November 2011 paper. It's question 5. Okay, so they say to us, a rescue helicopter is stationary, so that could be important, so let's keep that, which means velocity here is 0. So I'm going to write this in. Grade 12s, as I go through this, all the stuff I write everywhere, that's the sort of thing I would like you to start writing onto your exam papers, onto your question papers, because a lot of the times it's not that you don't know what to do, it's just the questions are long and they have lots of information, and then you struggle to pick out the information that's important. But if you make notes as you read it, it makes it a lot easier. Okay, so it's stationary. The soldier of mass 80 kilograms is lifted vertically upwards through a height of 20 meters by a cable at constant speed. So the helicopter is stationary, but the soldier is not. Okay, the soldier is going at 4 meters per second, but it's at constant speed. That tells me straight away constant speed means that acceleration is 0, which then tells me that F net is 0.2. Okay, that might be important. The tension in the cable is 960, so let's put Ft equals 960. There's no sideward motion. Brilliant. F friction is not to be ignored. So let me just quickly go over that. That was an important piece of information that I just wrote over here, okay? So Ft is 960. Now watch here. Now this we don't get often. Air friction is not to be ignored. Air friction is like friction on the ground, it's just upwards, okay? So let's look at the picture. There we go. We like this. Here's our picture. We're very happy. And what that means for us is that we realize it's going upwards at 4 meters per second. That was given earlier. Okay, let's see what the first question says. State the work energy theorem in words. Guys, you are going to get this. Looking through past papers, you'll even see today we're going to do it twice. The more papers you do, the more you realize this is one of those theorems I really like. It's really easy because it says to us that the net work done on an object is equal to the change in kinetic energy. It comes from the equation. The net work done on an object is equal to the change in kinetic energy on the object. Nice and simple. It's one of those easy ones which you can get from the equation. So let's go to question 2. Oh, now we get to the fun part. Draw a labeled free body diagram showing all the forces acting on the soldier while being lifted upwards. Guys, free body diagram number 1 means you've got to draw a dot as my object, and that's the soldier. Number 2, a free body diagram also means that you have to draw all your arrows going away from the object regardless of whether it's being pushed or not. If I had asked for a force diagram, then I can show arrows being pushing onto the object, but we want a free body diagram, okay? Secondly, this has to be a labeled free body diagram, which means you must write out the labels in full. Do not just put letters. Make sure that we understand what it is. Rather write longer labels and be on the safe side than write an F and go, well, you know, they'll know what it means. No, we won't. Okay, so let's go back to the diagram quickly. With my man, he is my object, okay? Cable's going up, that's easy. We've now got to say to ourselves, okay, he's a man, he has mass. That means he has to have weight. So his weight's going to act down. Okay, I don't care about the value right now, but they also said to us that air friction can't be ignored. Now we've got to decide which way does air friction work. So now we say to ourselves, okay, air friction is like friction on a surface. It always acts in the opposite direction to which the object is moving. So if the man is moving up, air friction must move down, which means air friction actually does that. Let's just call that air friction. Okay, so now we've got 3 forces. Now we go, okay, nothing moving him sideways. Those are our 3 forces. We now need to put these 3 forces into our free body diagram, okay? So let's do, there it is. Okay, has to start with a dot. So there we go. And we go, okay, we make it nice and neat. Let's look at screen as well. So there's the 960, that's going to go up. We'll label it in a second. We realize he has weight, which acts down, and we have air friction, which acts down. It's highly unlikely that air friction is going to be greater than his weight. You might need to work that out later on, and if it does work out to be that, oh well, then that's the case. You don't need to draw it longer, okay? But we can assume that it's not. So this would be my applied force. You could also call this the force of the cable on the man, okay? Anything like that. This one is the force of the air friction, okay? You could also say friction. Simple like that, that's easy. The other one is his weight. So we can call it weight, or we can call it the force of the earth on the man. Okay, full labels. Please don't write all sorts of little letters all over the place. Write it out. Okay, next one. Write down the name of the non-contact force that acts on the soldier during the upward lift. Out of these 3 forces that we've just drawn here, which one of these 3 does not actually touch the soldier? The cable is most definitely touching, so he's holding on, okay? Air friction goes against the man, so there's air, so that's definitely contact, but the man is off the ground, which means his weight is a non-contact force. So the way we'd write this is it's the gravitational force. It's a non-contact force, okay? You do not need to be in contact with the earth for it to have a force on you, which is a good thing, because if the force exerted by the earth went away, if we jumped up into the air, then we would float up into the air, and that would be bad. Okay, so we don't want to do that. Gravitational force. Now we get to the fun question. Use the work energy theorem to calculate the work done on the soldier by friction after moving through a height of 20 meters. Grade 12s, you may not use energy conservation theorems. You may not use equations of motion. Not that I'm sure I'd know how you would do it, but you can't. You have to use the work energy theorem. Okay? So now, if we remind ourselves what we know, first of all, we know that the applied force, which I'm going to call FAP, is 960 newtons. We know, well, we don't know, but we can find his weight, because that's mass times gravity, so we'll come back to that. What they're asking for is friction. He's going through a vertical height, so that's delta y, not delta x. Okay. He's moving at constant speed, so that means that acceleration is zero. It also means that there's no change in kinetic energy. This is actually the important part, because we need that to do the next part. Watch. My net work done is equal to my change in kinetic energy. The net work done on the soldier is going to be the work done by the applied force plus the work done by gravity plus the work done by friction. All three of those do work, and we want the net work, the result of all of them, okay? So applied force means that we're going to go F applied times delta y cos theta. Don't forget the theta. We're going to do the same with W, with FG, okay? Delta y cos theta. Watch what I'm doing here. I'm going to leave out this one. I'm going to go, because we want work done by friction, so I don't actually have to work out friction. So I want WF, and delta K is 0. We almost at the place where it's a mass issue. So my applied force, I'm just going to skip a little bit of space because I want to make sure I can fit it all in, is 960. It goes 20 meters. Applied force is up. The man moves up. Theta is 0. Fg is going to be m times g. So m is 80. G is 9,8. But, sorry, I forgot out the 20. Let's put a 20 in here quickly. Okay, 80 times 9,8 times 20 times cos. Now we think about it and we go, okay, hang on. He's going up. Air friction acts down. It's 180 degrees. They're in opposite directions. Plus WF equals 0. Now we just plug this all into our calculator. So that's 19,200 minus 15680. Okay. Now, it's minus because cos 180 is minus 1. So be careful. This means that now, if I take, this gives, here I get 3,520 plus work done by friction, which is equal to 0. So work done by friction is minus 3,520 joules. Minus is fine. I know work is a scalar. I know energy is a scalar. That minus says it's not useful. And in fact, what would happen is that energy, which is theoretically lost, actually turns into heat and friction and internal energy and all sorts of things. So don't worry about the minus. It's perfectly acceptable. Okay, we're okay with that. So, grade 12s. We have finished our first question. Lots in it, lots of theory. Okay, I need you to go take a break. Make sure you come back with your thinking caps because we're going to tackle a wonderful question in the next section. So I'll see you in a little while. Welcome back, grade 12s. Now we're going to dive into a really nice question. It's been adapted from the February-March 2011 paper, question 5. Now what we have here is we have a situation where we have a crate on a slope. Slope is 20 degrees. That's probably going to be important. There's a distance A to B. We're not going to worry about that right now. And at this point in time, the crate is stationary on the slope. Okay, so the crate is stationary. We're going to take it as that. And then they give you a diagram with a whole bunch of forces acting on it, R, S, and T. Then they ask you to label those forces. This is very similar to what we just did with the soldier, okay? S is the easiest, so let's start there, because S would be the force of gravity, okay? So we would say that S is the force of the Earth on the crate, okay? You can write it as weight, you can write it as gravitational force, it doesn't matter. T, okay, is a frictional force. It's the force of friction. How do I know that? Because the object is stationary on the slope. Remember that because it's on a slope, gravity is actually going to tend to want to pull it down. In order to not pull it down, there needs to be friction which acts up. So we can't ignore friction on this. Okay, so friction pulls the crate upwards. Has to be the frictional force. There is no applied force to the crate. R is now the fun one. R is your reaction force or your normal force, okay? Or we can say R is the force of the surface on the crate. Okay? It's the force of the surface on the crate. Instead of making you draw a free body diagram, I'm asking you to just label. All right, next one. Now it says to us, give a reason why R does no work on the crate. Well, let's look at the equation. W equals F delta X cos theta. Now, first of all, the crate's not moving, but let's ignore that, okay? Even if the crate was moving, R would do no work. Look here. R is at 90 degrees to the surface. If I put in whatever R is, the force, times whatever that distance is, and I've got to times it by cos 90 degrees. If you put cos 90 into your calculator, you're going to get 0. That gives me 0. So R does no work because it is perpendicular to the direction of motion. Okay? It is perpendicular to the direction of the motion. Can't do any work. We will do work from 0 to 89.9999% degrees, 90, no work. Start to do work again from 91. Okay, has to be at some sort of angle, but not 90 degrees. Okay, brilliant. Next one. Now, the crate now passes a point, so now the crate's moving at a speed of 2 meters per second. So over here it's going at 2 meters per second, and moves a distance of 12 meters before reaching point B lower down on the incline. Great. Calculate the net work done on the crate during its motion from A to B. Now we're going to go, okay, we can do this. Let's first realize we need some more values, okay, to do this. So we go, okay, first of all, what we missed out earlier is that friction is actually equal to 190 newtons. Okay, it's experiencing a friction of 190 newtons, and the crate has a mass of 70 kilograms. We need that information, okay? So crate has a mass of 70 kilograms. Friction 190, mass is 70. Now we're going to go, okay, it's moving down at a constant speed, so we want net work done. It's not going to be 0, but we don't know what the change in kinetic energy is, so we can't do that yet. But what we do realize is the net work done will be equal to the work done by gravity plus the work done by the frictional force. Okay. How are we going to make our lives easier? So we go, okay, let's go back to here, and on here we go, remember that I can convert S, gives me, I have a parallel component to S, okay, and I have a perpendicular component. Let's make that so it looks actually like what you'd use in maths, because that's going to be a bit easier to understand. So let's do it this way. Sorry. FG parallel. That pulls it down. The work done by FG parallel and the work done by T, if I add those together, I get my network. Okay? That's how I get my network, because I'm adding the two together. Because net is just an addition, the result of them. So now we've got to remember, okay, I'm looking at, FT is easy, it's 190. We know it's cos. We'll decide cos in a second. We'll do the angle in a second. We know that it goes 12 meters. That's not a problem. FG parallel becomes the problem, because I know the mass is 70, so I know FG is going to be M times G, so it's going to be 70 times 9,8. We'll get the answer in a second. So we go, okay, that's cool. But I'm not looking at straight FG, I'm looking at FG parallel. So we go, okay, now we've got to remember that FG parallel is equal to weight times sine theta. This theta, now we get all, because we love the fact they use theta for everything, that theta is the angle of the slope. Okay? The angle of the slope. You need to learn this. Please learn this. If I was looking for the perpendicular component, because say I wanted the normal force, then I would use cos theta. So please, 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 I'm begging you, learn that it's sine theta. It's very important. So how does this affect the equation? Well, FG, we're actually going to use the parallel force, delta x cos theta, plus friction delta x cos theta. We just said that FG parallel is let's make our lives easier, FG sine theta, so that means it's actually mg sine theta. So watch what I'm doing, mg sine theta times delta x times cos theta. Now, I haven't added any numbers in yet, grade 12s, because what I'm doing is I'm setting up my equation. You are more than welcome to work out FG parallel separate and then substitute it into this equation straight away. That really is up to you. By doing it this way, we avoid carry down errors, which is the first thing, and two, it avoids a lot of errors when it comes to the decimal points, because decimal points often become a bit of an issue, okay? And where do we round off? Because we need to round off at the end, but we actually round off to 2 decimal places at the end of every single sum if it's a separate sum. So, let's just make it easier. Okay, so what do we know? M is 70, G is 9,8, because that hasn't changed. Sine 20 degrees. They said to us that it goes a distance of 12 meters. Okay, now we've got to decide on theta. The cos theta in the work is not this angle of the slope. This is when we've got to go, okay, parallel force is acting down the slope, the body is moving down the slope, they're in the same direction, theta is 0. Okay. Run out of space, you do this all on one nice line, okay? Be careful. Friction, I told you, was 190. X is 12. Now we need to make a decision about cos. So we go, okay, hang on, wait. The object's going down the slope, but friction acts up the slope, so it's at 180 degrees to each other. Okay, so we put all of this into our calculator and we get 2815,51 minus 2,280. Now, what that gives us is a final answer of 535,51 joules. What does this mean? This actually means that our crate is accelerating down the slope. It is getting faster. If network was 0, okay, then that would imply that the velocity stays the same, okay? It is accelerating down the slope. The force of gravity is stronger than the frictional force. Change in kinetic energy is definitely going to be an issue here. Positive, that means it's not slowing down. That means it's not losing anything to friction, but work is being done on this crate, and it is useful work. We can do something with it, theoretically. Okay, next one says to us, oh, look here, because we've already done this today. Write down the work energy theorem in words. Now, we've done this once already, and what did we say? The net work done by an object is equal to the change in kinetic energy of that object. The net work done by an object is equal to the change in the kinetic energy of the object. Same question, February, November, same year, okay? They're going to ask you this one. Now let's get to the fun part, because now we need to be able to use it. This is a little bit of a hint for you. Isn't necessarily true, but a lot of the times grade 12s, what I've noticed is if they start to talk about the work energy theorem and they ask you to state it or give you something to do with it or anything they work around it, you're probably going to have to use it, okay? Because watch here. Now they said, use the work energy theorem to calculate the speed of the crate at point B. Okay, so work energy theorem says to us that W net equals change in kinetic energy. We have worked out W net, okay? We just worked it out, 535,51. Delta K means final minus initial. If you need to write this to remind yourself, then please do. I'm still going to set up the equation before I do anything else. So that means I've got to do a half m final velocity minus a half times m times initial velocity. Once again, if you want to work out your initial kinetic energy separately and then do it in a whole bunch of separate equations, you're more than welcome to. But please, grade 12s, I'm begging that you actually make it really, really clear what you're doing, because if we can't find stuff, we can't give you the answers, and it's got to make logic sense. So, work net, 535,51. Mass, well, that hasn't changed. It was 70. I want final velocity. Mass is still 70, and initial velocity is 2, because they told you that it's going at 2 meters per second when it reaches A. What have we got? Now we have a mass problem, grade 12s. That's all it is. You've done the science is over. Now we really see if you can use a calculator. Guys, take your time. You have more than enough time in a test or an exam to do this. A half times 70 is 35. So then we have a half times 70 times 2, so it's a half times 70, which is 35 times 2 squared, which is 35 times 4. It actually gives me 140. Okay, so now we're going to take everything to the other side. We want VF squared on its own, so we've got 35 VF squared. It's minus 140, so when I take it to the other side, I'm going to add it. Okay, so we're going to go 535.51. We're going to add 140. Okay, which is 675,51. Now, guys, I could have done that in my head, but what I want you to see by using the calculator is that please use the calculator. You have a calculator, use it, make use of it. Otherwise, you really are going to get yourself into trouble, and there really is no reason for that. Okay, but we want VF squared, we want VF, okay? So first thing I'm going to have to do is divide both sides by 35. So we've got 675,51, divide by 35, and we get 19,3, okay? So that's 19,30. We want VF, so V, okay, we go here, and we say, okay, let's take my answer. I'm going to square root my answer, and we get 4,39. So my final answer, 4,39 meters per second. And we say, well, does that make sense that it's sped up? Of course it does. 12 meters is actually a really, really long distance. Well, it's not really, really long, but it's quite a big distance. The diagram makes it look really small, but think about an object falling for 12 meters. That's a couple of stories. That's a long distance. It's going to speed up because gravity is acting on it. I want to show you another thing. Now, we got 4,39. If I didn't use my calculator and use the answer, but I went, okay, let's look square root of 19.3, I get 4,39 as well. So slightly different out on the decimals, but that's okay, grade 12s, because we want you to write all your answers to 2 decimal places. Please be careful, because I see this all the time, is you write all the decimal points, you're actually going to lose marks for that. You must obey the instructions, which says round off to 2 decimal places, okay? Now, grade 12s, that was a bit of a doozy. That was a nice question because I asked you a lot of stuff about force diagrams. We realized whether you understood what network was. They led you. They could have been really, really horrible and started with 2.5. If the examiner is feeling particularly mean, they can start at 2.5, telling you to choose the work energy theorem. And then you've got to remember to minus the forces and stuff, okay? So, we've had a great second session, so we're going to take a little bit of a break, grade 12s, and when we come back, we're going to tackle another really, really nice work energy and power question, so I'll see you in a little while. Welcome back, grade 12s, and now we're going to tackle another question, still dealing with work energy and power. I like this question because now we add a little twist to the network equation. This is from the February-March 2009 paper. Okay, it's question 6. It's really, really nice. It says to us, in South Africa, the transportation of goods by trucks adds to the traffic problems on our roads. A 10,000 kilogram truck travels up a straight inclined road of length 23 meters at a constant speed. That means no acceleration of 20 kilometers per hour. And we go, hang on, wait, we can't use kilometers per hour. We're probably going to have to change that to meters per second just now, so we'll leave it. The total work done by the engine to get the truck there to the top is 7 times 10 to the 5, that's to the 5 joules. The work done to overcome friction is 8,5 times 10 to the 4. So total work done, that would be your total, that's the engine's not net, okay, is 7 times 10 to the 5. That's work done by the engine. So let's actually call it that rather, not total, because it's work done by the engine. So let's do work done by the engine is 7 times 10 to the 5 joules. Work by friction is 8,5 times 10 to the 4 joules. And it's work by friction, so it's going to be negative because we have to overcome friction. All right, so 23 meters, it's a relatively long space. Okay, and here's our truck, goes up, goes through a height of h. Now, oh boy, look at that. Calculate the height h reached by the truck at the top of the road. They just dumped us in there straight away. I want to know what's that height. Very important thing was said here. Constant speed. Constant speed means that your acceleration is 0. It also means that the net force acting on your object is 0. Okay? But net work can't be 0 because it's going through a height. So watch here. And also, they didn't tell us how much work gravity does. That's what we're missing, is the work done by gravity, okay? If I knew the work done by gravity, then it would be actually really easy because the work done by gravity is the changing potential energy, but they never gave us that. So, let's go here and we say, okay, well, we know that net work is changing kinetic energy, but this thing doesn't have a change in kinetic energy because it's constant speed. But it does have a change in potential. So let's look at the change in potential. So change in kinetic plus the change in potential. Remember, U is EP. U is EP, it's the same thing, okay? So my net work is equal to my change in kinetic plus my change in potential. My net work is going to be the work done by my engine, okay, plus the work done by friction, which we're okay with. Delta K is going to be final minus initial plus final minus initial. We're doing okay so far? My engine, we said, gave me 7 times 10 to the 5. Friction has to be in the opposite direction, so it's negative work, so it's 8,5 times 10 to the 4. Change in kinetic energy is 0 because the initial and the final are the same value. So velocity didn't change, so we don't even have to write in the equation, we can just write it as 0. Now we go, okay, hang on, wait. Final potential is what we're actually looking for, so that's mgh. Initial potential, oh wait, doesn't have any height. So what's the initial potential energy if we look at the equation mgh? 0. Okay, so minus 0. Oh, look at that. Doesn't this look like something we can handle? Of course it does. So we're going to go 7 to the power of 5 minus 8.5 to the 4, and we get 615,000. And they told me the mass of the truck was 10,000 kilograms. It's actually very, very heavy. So 10,000 kilograms. Gravity is 9,8. That hasn't changed. And look here, we want height. Okay, so we have 615,000. 10,000 times 9,8 gives me 98,000. We want HF on its own. Okay, so we divide both sides. So I've already got the 615,000 in my calculator. I'm going to divide by 98,000. And we get 6,28. 6,2755. We need to round it off. That means we go to the next, we round it up because of the 5 at the end, okay? 6,28, it's not going very fast. It's going 20 kilometers per hour. It's only going up, it's a very, 20 degrees for a truck is very, very high. Okay, you guys have, I hope, have at some stage, not that I'd want this to happen to anyone, is you've gone somewhere on a trip and you've ended up on a hill and you're stuck behind a truck. Okay, the sheer mass of the truck makes it very, very difficult for it to get up those hills, okay? And the hill, the steep incline doesn't help. Remember, the engine of a truck has a set amount of work that it can do. There's only so much it can do. And that engine has shown it's got to overcome friction, it's got to overcome gravity and all sorts of things. So we need to make sure we get this, that we understand 6,28 is not very high, but it's okay. So, next question. All the same information, but now they say to us, like this question. The instantaneous power delivered by the engine of the truck. Okay, now we've got to go, okay, power has two equations. Power is work divided by time, it's change in time, or power is force times velocity. It's worth 6 marks. We've got to say to ourselves, okay, did we anywhere get told how long it takes to get up the hill? Let's have a look at that. Transport, we've got 10,000 kilograms, we've got 23 meters, speed, joules, no time anywhere. That means can't use power equals work over time. That means we have to use P equals V times F times V. Okay, first we go, we can use this equation because remember, we can only use power equals force times velocity if it's going at constant velocity, and it is. So that's great. We know V. So let's start there and go, okay, my V was 20 kilometers per hour. Can't use it in kilometers per hour. Must be meters per second. Little trick. You don't have to show the conversion, but make sure you write this down somewhere. To go from kilometers per hour to meters per second, we times by 3.6. To go from meters per second to kilometers per hour, we divide by 3.6. So we times this by 3.6, sorry, other way around. Divide by 3.6 to get to meters per second, times by 3.6 to get to kilometers per hour. So let me show you. 20 divided by 3.6, 5,556. Okay? 5,56 meters per second. Great. I've got the first part of my equation. Yay, very, very happy. Now we need force. Okay. They want the power of the engine. What do I know about the engine? I know the work it does. I know it does 7 times 10 to the 5 joules. Okay. I know it goes 23 meters. So, work done by the engine is equal to the force of the engine times the distance it travels times cos theta. Okay, great. Work done by the engine, 7 times 10 to the 5. Force of the engine, that's what I want. So let's write that just with a little e for now. It went 23 meters. Because, well, the engine's pulling it up the slope. Because going up the slope, theta is 0. Great. So that tells me that 7,5 times 10 to the 5, 23 times cos 0 is 1, so it's 1, is 23 times the force of the engine. I divide both sides by the force of the engine, which is the distance. Ooh, look, it's a nice big number. Okay, so we get 30434, 30434,78 newtons. Okay, so I have force now. Yay, we can do this because now we just need to plug it in. That means power is force times velocity. My force is 30434,78. My velocity was 5,56. And we're going to go 30434.78 times 5.56. And we get 169,000. Okay, let me just see it again. 217,38. And that's measured in watts. Grade 12s. You are more than welcome to do it, to put the calculation for force into your power work equation. So what I'm saying to you is, if work equals force times delta x cos theta, then force would be delta x cos theta over w. Okay. We took the velocity and divided by 3.6, so I could have actually written the power equation as this. It's force times velocity, so that means it would be delta x cos theta divided by work done times my velocity divided by 3.6. You're more than welcome to do that, grade 12s, okay? So you're more than welcome to go along, do a real equation like this, and then substitute everything in. For something like this, I'm going to suggest you don't. It's not like the work equations where it's quite easy to put a whole bunch of stuff together and work it out from there. Simply because now we start to ask for trouble, because if we've, say, manipulated the equation for force wrong, which happens, and we go force equals work divided. In fact, I've done that. I've done exactly what I don't want you to do. I hope you'll realize that and go, well, actually, that's nonsense, Tracy, and it is nonsense, because force is actually work divided by delta x over cos theta. If I now saw this as a marker and I saw this, I have to stop marking because it's wrong. Okay, it's a real problem. That's it. You get the equation, you get the mark for P equals FV, but you don't get anything else. So please be careful with that. I would much rather you did it this way around, where you work it out, and then say in this step you go and divide by 7,5 times 10 to the 5. You take 23 and divide by 7,5 times 10 to the 25. First of all, bells should ring in your head because you're going to get a ridiculously tiny answer. So bells should ring in your head and go, okay, I've made a mistake. Let me go look at it again. If the work is this big, the force must be very big. Okay? So it's a good way to check. Okay. Now, we have one more question to this. Still the whole thing, and that says, arrestor beds are constructed as a safety measure to allow trucks to come to a rest when their brakes fail while going downhill. Write down 2 design features of such arrestor beds. Now, what if you get to this question and you go, I don't know what an arrestor bed is? Guys, look at the hints in the question. It's a safety measure that allows trucks to come to rest when their brakes fail. So in other words, it's something built into the road that a truck driver can drive into that will help him stop if his brakes can't. So it's got to be an area on the road that will resist the truck's motion. That's what we mean by arrestor beds. You guys okay with that? So let's now think carefully. It says give 2 features that we would need in such arrestor beds. So now we've got to go, okay, well, there's a couple of things. I've already mentioned one. It's got to be made of something that's going to resist the truck's motion. So we go, okay, can't be tar. That would be silly. Can't be mud per se, because what if it doesn't rain? What does the mud turn into if it doesn't rain and the water evaporates? It becomes sand. Okay, so a good thing is something like sand that will cause friction on the truck's tires. So the first thing is we need to cause friction. So we've got to think carefully, and there's obviously lots of possibilities. Make sure it's practical. So, for example, sand to prevent the truck's motion. Second thing, the truck's not going to stop in a meter. So to have it only a meter long is stupid. Okay, trucks are longer than meters. You know this. The truck will be going relatively fast if its brakes fail while going downhill. The truck is also heavy. Lot of inertia. So we need to make this arrestor bed long enough that there's enough time for the truck to stop, that the friction acts over a long enough distance to get it to stop, to change its inertia, to get it to stop moving. Okay, so the 2 things we need is it would need to be sand, something with lots of friction, and the second thing is it would need to be long enough to stop the truck moving. Okay, sometimes on the road, it's also, I'm sure, I hate going over these things, when you're on the road you have those lots of little humps on the road. That's also to stop, it's to slow you down. Okay, those also help, but the friction, the sand is better. Okay, now grade 12s, we have done a lot of work today. I know we only did 3 questions, but we covered a lot of different sections in the curriculum, things that you're going to ask, little tricks. Work, power, and energy, one of the sections you're guaranteed to get. Practice, practice, practice. Find as many possible questions as you can. Okay, very, 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 very important section. And grade 12s, that is where I'm going to call it a day. We've gone through work, energy, and power, and this is where I say goodbye, and I will see you again next time. The net work done on any object is equal to the change in kinetic energy. Some of you might have learnt it as change in EK. That's fine. K is the symbol that's on your information sheet at the moment. Guys, that's very, very important because you're going to get it. Kinetic energy, remember, changing kinetic energy means I've got to do kinetic energy final minus kinetic energy initial. Okay, any change in, whether it's in equations of motion, momentum, whatever the case may be, it's always final minus initial. That's very, very, very important. Okay, so are you guys ready to jump into the first question? It's actually a really nice one. It's taken from the November 2011 paper. It's question 5. Okay, so they say to us, a rescue helicopter is stationary, so that could be important, so let's keep that, which means velocity here is 0. So I'm going to write this in. Grade 12s, as I go through this, all the stuff I write everywhere, that's the sort of thing I would like you to start writing onto your exam papers, onto your question papers. Because a lot of the times it's not that you don't know what to do, it's just the questions are long and they have lots of information, and then you struggle to pick out the information that's important. But if you make notes as you read it, it makes it a lot easier. Okay, so it's stationary. The soldier of mass 80 kilograms is lifted vertically up, as you'll even see today. We're going to do it twice. The more papers you do, the more you realize this is one of those theorems I really, really like. It's really easy because it says to us that the net work done on an object is equal to the change in kinetic energy. It comes from the equation. The net work done on an object is equal to the change in kinetic energy on the object. Nice and simple. It's one of those easy ones which you can get from the equation. So let's go to question 2. Now we get to the fun part. Draw a labeled free body diagram showing all the forces acting on the soldier while being lifted upwards. Guys, free body diagram number 1 means you've got to draw a dot as my object, and that's the soldier. Number 2, a free body diagram also means that you have to draw all your arrows going away from the object regardless of whether it's being pushed or not. If I had asked for a force diagram, then I can show arrows being pushing onto the object, but we want a free body diagram, okay? Secondly, this has to be a labeled free body diagram, which means you must write out the labels in full. Do not just put letters. Make sure that we understand what it is. Rather write longer labels and be on the safe side than write an F and go, well, you know, they'll know what it means. No, we won't. Okay, so let's go back to the diagram quickly. With my man, he is my object, okay? Cable's going up, that's easy. We've now got to say to ourselves, okay, he's a man, he has mass. That means he has to have weight. So his weight's going to act down. Okay, I don't care about the value right now, but they also said to us that air friction can't be ignored. Now we've got to decide which way does air friction work. So now we say to ourselves, okay, air friction is like friction on a surface. It always acts in the opposite direction to which the object is moving. So if the man is moving up, air friction must move down, which means air friction actually does that. Let's just call that air friction. Okay, so now we've got 3 forces. Now we go, okay, nothing moving him sideways. Those are our 3 forces. We now need to put these 3 forces into our free body diagram, okay? So let's do, there it is. Okay, has to start with a dot. So there we go. And we go, okay, we make it nice and neat. Let's do upwards through a height of 20 meters by a cable at constant speed. So the helicopter is stationary, but the soldier is not. Okay, the soldier is going at 4 meters per second, but it's at constant speed. That tells me straight away constant speed means that acceleration is 0, which then tells me that F net is 0.2. Okay, that might be important. The tension in the cable is 960, so let's put Ft equals 960. There's no sideward motion. Brilliant. Air friction is not to be ignored. So let me just quickly go over that. That was an important piece of information that I just wrote over here, okay? So Ft is 960. Now watch here. Now this we don't get often. Air friction is not to be ignored. Air friction is like friction on the ground, it's just upwards, okay? So let's look at the picture. There we go. We like this. Here's our picture. We're very, very happy. And what that means for us is that we realize it's going upwards at 4 meters per second. That was given earlier. Okay, let's see what the first question says. State the work energy theorem in words. Guys, you are going to get this. Looking through past paper. Welcome grade 12s. Today we're looking at work, energy and power. That section we know that when it comes up in the exam you go, no, I hate this section. It's actually a really, really nice section. You are going to get it. And remember, the thing that we're really, really harping on at the moment is the work energy theorem. So quickly, before we go into the actual questions that we've got planned, I just want to remind you of some things. So remember, work and energy are pretty much interchangeable. Work is defined as a force times by a distance cos theta. Remember, the angle that the force acts on is very, very important. Energy is defined as the ability to do work, and then of course power is the rate at which work is done. Now power, you have two equations, power equals W over T, and you have F times V. F times V is actually a nice equation, but it is only valid when you have a constant velocity. If the object changes velocity, in other words, its kinetic energy changes, you cannot use P equals FV. Be very careful, they're going to try and trick you out with that one, okay? Then you have to use W over T. For the work energy theorem, and this is the one that we know you guys don't really like, work energy theorem says to us that